Good afternoon, ladies and gentlemen. My name is Sen Hu. I'm the coordinator of the webinar event. Welcome you all to attend our April 21st, 2021 CGS webinar. And today we are going to have an opportunity to have a presentation discuss about the physical and the mechanical property which in the GTA, the soil, and will be presented by our two gentlemen, Dmitry Olshansky and Jeffrey Krier. So before we go to the event, just continue, just as usual, just like to give you some idea about the coming event. And the first, also like to thank for all the 10 sponsors for this event, including the Geosoft, Keller, Wood Canada, Brown Engineering, the Burkhardt Group, Issue Wood, the Maynard Canada, Boulder, EBS, and the Red Sea Stone. Thank you for your supporting, and I do hope you continue supporting for the future events. And as we know, the Geo Niagara Falls the conference is coming, which will be held between September 26th and the 29th in Niagara Falls. But currently, we haven't received the formal announcement. How do we carry out this conference? So just be patient and wait for the first notice about. And I know some of you are preparing the paper to be presented, so you're welcome. And we are going to have our annual event on May 13th, and also at the same time at the noon between 12 and 1:30 p.m. on the day. And it's our honor to invite Mr. Gary Seder to give us a presentation talking about the innovation of the helical pipe shaft optimization. I think it will be the same. It will be very interesting topic because he's working in the industrial. I'm sure he's going to give us not only the design theory, but also many practical cases. So that's and the registration of the event will be announced soon. So just wait for your email notice. Then once it's open, please register as many as possible. And as we know that today there are more than 330 registered for this event. So I'm sure people are waiting for this interesting topic. So now it's my pleasure to have an introduction and make a brief introduction for our two speakers today. And the topics is physical and mechanical property of the soils in the Greater Toronto area, and presented by Mr. Dmitry Olshansky and Jeffrey Krier. And as we know, I think some of us, some of the attendants, you are involved in the subway project in GTA. And since the past 7 years, the extensive geotechnical investigation and the laboratory testing program has been carried out for some reason the transit project in Toronto area. So, and they are mostly in charge by TTC. So And that's a reason why we invited two gentlemen from TTC to give us this presentation of the webinar, to give us some summary about some soil consideration classified by the TTC's soil groups classification, and also they are going to present some results carried out by advanced tests, and also they are going to make kind of the comparison between between the from the result of those advanced tests, and give us some good indication and advice and advices for the geotechnical work in this area. And Mr. Dmitry Olshansky, I think many people know him, and he holds a master degree, master engineering of the civil engineering from the University of the Waterloo. And he also got a Master of the Science degree of the Geotechnics and Hydrology from Moscow University. And before he joined TTC in 2008, he has been involved in many international projects, including the geotech and the geo-environmental engineering work. And after he joined TTC in 2008, he has also been involved in several major infrastructure expansion projects of the subway system. So that's a kind of the history as we know him. And Mr. Krier, he is also senior engineer of the TTC, and he graduated from the civil engineering department of the University of Toronto. And he joined TTC just 1 year after Dimitri. And after he joined the TTC, he has also been involved in a variety of the geotech and the geo-environmental engineering works, and especially including some design and construction work for the micropipe and the helical pier design and the testing, as well as groundwater control and the dewatering tasks, which are part of the important thing in the subway project. So now let's welcome two gentlemen to give us this presentation. Thank you.
I'm hoping everybody can see my screen.
Yes.
Okay, so we'd like to talk a little bit about the physical and mechanical properties of soils in the Greater Toronto Area. Sorry, I'm just having some trouble with my computer here. Oops. So we like to. So we want to start with some. Yeah, here we are. Sorry about that, everyone. So we're going to start with some physical and mechanical properties of the soils in the Greater Toronto Area. What we're going to do is there's a bit of an outline of our presentation. We're looking to define what the physical and mechanical properties are. We're going to talk about some of the goals of what we've been working on here at TTC, what some of our source data is, what the soil groups we classified our soils and how we classified them, how they were established and confirmed, what some of the physical properties are. I mean, we have a wealth of data that we've got, some of the recent developments. We've recently had some issues with some of our classification system. Then we want to touch base on some of the mechanical properties. We've got a summary chart showing some consolidation results. And then we want to focus in on some track seal testing and the track seal analysis that was carried out. We did some comparison of the various methods to analyze the results. And we also want to go into some of the ideas of what the industry is currently using and what's being recommended for design and how they compare with our results. And then we want to touch a little bit on our database and some of the, we're calling it misclassification concerns that we've encountered. So talking about physical and mechanical properties, our physical properties, we're looking at soil distribution, grain size, plasticity index, density, dry, specific gravity, bulk density, the typical moisture content, etc. These are some of our more routine tests and indicative tests that we use. Everybody uses these. They're very consistently used throughout the industry. Some of the mechanical properties that we're talking about are, we've defined them more along the advanced laboratory testing, where we're looking at strength of material, triaxial tests, compression tests, shear tests, compressibility tests. So that's kind of the route that we've taken with our physical and mechanical definitions. So we're going to start here with our introduction. Many of our projects at TTC, we do have a lot of small sites that we do a lot of work with. We also have our projects with limited budgets, and that's pretty consistent throughout the industry. You have small projects, but also larger projects, and we all carry out routine characterization testing. The advanced testing, when it is carried out, many times, coming from a consulting background, I know it's very difficult to encourage a client to spend $2,000 or $3,000 on a single test, especially a triaxial test. So those are usually carried out, we find, in limited numbers, 2 or 3 at most, depending on your project budgets. Most times I find when I was working in consulting, it was consolidation tests that you could try and get carried out. The end result that we're finding is that engineers and designers, we tend to resort, or we find people resort to more empirical relationships, what your experience is, and what's been published in previous textbooks, papers, manuals, etc. Some of the concerns we've raised with these are how relevant are these parameters to the soils that you're looking at? Is a soil from somewhere in Europe or in Asia relevant to the Toronto area? Perhaps they are, perhaps they're not. It's hard to say. How many tests were carried out? Are they statistically significant? Are you looking at a paper that may have 6 tests carried out, or did they carry out a number of 20 or 30 tests? Were the authors very conservative with the numbers, and did they remove the higher numbers? How good are the results? And how were the soils classified is another one that we keep looking at. Sometimes there's a variation between consultants, and we find even in our own projects, 2 consultants, can go to the same drill site, and they will come back with varied soil parameters and soil recommendations. Even down to the description of the soils can be different as well. So our ultimate goal in what we're doing right now is we want to have a consistent method for grouping our soils for all of our projects. We're in the process of creating a database of both physical, mechanical, and eventually we're going to look at including some of the hydraulic properties for each soil group. And then we're going to continue to compile and add to this database over time. One of the things we also have to try and do is monitor and ensure that the soil groups are consistent and maintained so that we don't get crossover. So our data sources for this, some of the more well-known projects is the Relief Line South and then the Scarborough Subway Extension. Both of these have since been transferred to Metrolinx. So we're going to start with our soil grouping. We established our soil grouping using grain size and Atterberg limits. Our initial assessment was on over 600 tests from our own projects throughout the city of Toronto, and we established 7 groups. You can see them on the right side of the screen there, G1 through G7. We did create 2 column subgroups. We called a cohesive group and a non-cohesive group. So within the glacial tills, you have cohesive and non-cohesive glacial tills. And as we moved down through the projects, we found that we also had cohesive and non-cohesive silts. So we broke the group 5 into a non-cohesive and cohesive material. Like I say, initially the system was used for our 2 major projects, the Relief Line and Scarborough Subway Extension. But since then, we've expanded it to use it for all of our projects and all of our investigations. And it is allowing us to consistently organize the soils and to organize all of our lab results. One comment we have, though, is that this soil group, it's established for our glacial deposits only. They're not reflective of the properties of lacustrine or creek deposits. If you're working anywhere down near the waterfront, any creek deposits, close to creeks, etc., these soil groups will not work. We're still working on and looking at how we're going to classify those soils. But these are primarily for the glacial materials that you'll encounter in Toronto. So here's some of what we looked at. The thick black lines were our initial, call it kick at the can. These are based on our 600 grain size. Then you can see the relief line and Scarborough results are the multicolored lines. And we get fairly good agreement from our initial kick for sands and gravels. There's a little bit of spread going beyond the lines. And then for the silty sand, sandy silts, we had fairly good agreement as well. We also did the same thing with our non-cohesive glacial tills and our cohesive glacial tills. And you can see that they bounce around a little bit. So based on our initial 600 grain sizes, we were able to revise and modify our envelopes for these. And this is what we ended up with. So in this area, let's see if I can get a laser pointer. There we go. So up in this area, we have our group 1, which is our sand and gravels, group 2 on this side, and then we've combined them where we have our grain size with our Atterbergs for each group. So this is the non-cohesive, followed by the cohesive glacial tills, group 4 being the silty sands, and then we get progressively finer until we get to our group 7 down in this area, which is the clays. So we get into the clays. Now, with the physical properties, because we had such a two large major projects, and we were able to combine everything and get a really good idea of soils and what their properties are and their physical properties. So we've come up with a number of charts that you can see here for moisture content, for example. This is all of our soils by group, starting in the upper left for group 1 being sands and gravels, all the way down to clays in the lower right, G7. These charts are based on about 8,000 to 9,000 tests in total. So in both projects, we did a moisture content on every single soil sample that was pulled out of the ground. And this is our result. So we have a pretty good feel now for moisture content of the glacial soils in Toronto. We also did the same thing with our bulk densities. You can see here the physical properties for bulk densities, and we have about 500 tests in these ones here. And we have a really good feel for what materials are and what the bulk density is. So some recent developments that we've had, portions of the downtown relief line and some recent investigations carried out at Queens Quay for the waterfront LRT modifications, as well as at Greenwood Yard and Russell Car House. We did have, oops, things are moving a little bit here, sorry. We did have some issues with our group 5C, which is the cohesive silt, and the plastic limits for G6. So what happened is the materials, they represented, or they plot out under a 5C or the silts, but they behave more like a group 6, which is in the plasticity side. And I'll show you this in the next one. And basically, this is where I was saying earlier that it's our opinion that this is the lacustrine soil deposits, okay? And, whoops, sorry, something's happened. But here's where we are now. So we have the glacial soils. This is our initial kick at what we said for our group 5. And you can see here our group 5 for the silty clay, it's group 5 cohesive, is down in this range. When we plotted out those lacustrine deposits, we tend to get higher, good agreement here. It's a little bit higher down in this area. But then when we plot out the plasticity, it plots in this area, which is more of a better fit with the G6. So at the moment, we're still on the debating how we can classify these materials. So just stay tuned for that. And like I say, we do find that down in the waterfront and anywhere where you have a lacustrine deposit, you're getting those changes. We're going to talk a little bit more about mechanical properties and our focus. So these are our mechanical properties from our definition. And we've grouped our mechanical properties based on our physical properties. So here we have our consolidation results from our consolidation tests. And we're showing here our group 5, which is our silts, clay silt materials, and these are the cohesive materials, our silty clays, and our cohesive tills. And we've got a number of values that we're hoping will create a good database for us to use in the future. What I'd like to focus on now is some of the triaxial results. You can see a couple of different machines here, and my colleague down in the lower left working at one of those machines. So with the characterization tests, just to give you an idea, actually, just as an aside, just to give you an idea of the number of tests that we were looking at, you can see here that the characterization, we had about 1,200 gradations and 800 Atterbergs that we included in our summaries. And our advanced testing has about 180 sets of triaxial tests, or about 540 specimens. This is a combined for both the relief line and the Scarborough subway. And we think this is enough data that we can be fairly statistically significant, if I can say that right. So our triaxials, we're going to go through some of the techniques that we used here. So we used 3 different approaches to assess our triaxial results. Okay. You can see some of them here, and they're outlined in the next pages. We looked at individual tests. We looked at combining all the tests under the same soil group. And then we looked at using all of the tests combined using the stress path. And here's our first one. So we would do a set of triaxial tests. We would come up with our Moore circles, plot them out, come up with a cohesion intercept, friction angle, and then we would add that to our database. What we did subsequently is we grabbed all of our tests by soil group. So we classified all of the soils based on the physical properties, especially the grain size and Atterbergs, and our visual assessment. Using that classification, we came up with, and we're able to plot out, and we got fairly reasonable agreement here. This is for our Scarborough project with group 2, so this is the sands, and then the downtown relief line as well. And I can't recall how many tests we had in here, but we had a number of tests that we were using. This is the second method. And then the third method was we looked at all the deviator stress. We plotted everything out for the stress path method to come up with these values. And our intent here was to ensure that all 3 methods gave us a consistent numbers. So, and then again, what did we find? There was a little variation amongst the methods used. So for our downtown relief line for the G4 soils, which are the silty sand, sandy silts, when we used the Moore circle, we were getting something in around 45 degrees. And then when we used the stress path, we were getting about 48 degrees, so somewhat higher. And then we also found that the cohesion was not equal to 0, okay, at certain points. And you can see here we have the Scarborough soils, which is the G6. We were getting a friction angle, so this is a silty clay material, or clay silts. We were getting about 37, so we had good agreement there. We do have a cohesion here, but we didn't get one on using the stress path. So then what we did is we looked at and said, okay, how do our results compare between Scarborough, our work at Scarborough, and the relief line south? And where do we stand with these? So we looked at and summarized all of our results by method. And you can see here we have our Moore circle summary, our stress path graph summary. Okay, and we did it by Scarborough as well as the relief line south. Okay, and we found that the average friction angle between the 2 sites varied by 2 or 3 degrees. Okay, there was some variability in the cohesion between the 2 sites as well. The cohesion varied depending on how the tests were analyzed. Was it a more circle analysis, or did we do it through using stress path? Since we had reasonable agreement with the friction angle, we figured that we could combine our sites and combine these materials into one soil group. So we took the G1 from both sites and combined them into one master table. So that gave us, like I said before, that gave us about 500 test results that we could use. And this is here, you'll see, is a summary of all of our results. We outlined by soil group 1 through 7, the peak friction angle, the cohesion value, and we've also included in this table the bulk density and the moisture content. So we've given an average value, what were our minimum and maximums, and what's the standard deviation. Okay, so for the non-cohesive soils, groups 1, 2, 3N, 4, and 5N, the average friction angle actually ranges from about 40 to 43 degrees. You have a standard deviation of a couple of degrees. For the cohesive soils, it's the glacial cohesive material, the cohesive silts, and the silty clay. The average friction angle ranges from about 32 to 33 degrees, and we got a standard deviation of about 4.5 degrees. Let's call it 3 to 4 degrees. The variability in the cohesion, there was results with standard deviation. There was some variability, in the cohesion, and we did have some standard deviations ranging from about 16 to 35 for those cohesive materials. One of the interesting things we did with our two projects is we did a sample method comparison. So in the initial stages of the investigations, we were using and obtaining samples using both the PQ method and a sonic method. What we found interesting was that the samples returned from the sonic samples. Oops, something happened there, sorry. Let's go back to here, there we go. So apparently my computer is done something weird. Hopefully that doesn't.
Technology, what can we do?
Yes, exactly. So something's happened there, and I'm hoping this comes back. So back to our sampling. Yeah, so initially during the investigation, we were doing our sampling using PQ, and we were also doing sonic testing or sonic sampling. What we found, and you can see it here in the lower left, is that the samples returned from the sonic rigs, they were relatively good quality, and we thought they might be good candidates for doing triaxial testing. But we did have some concerns before we did any of that, before we relied heavily on the sonic samples. First of all, we were concerned that there was some concern that the material may have either loosened during sampling because it's a vibration process, or it may have actually densified. There was some people, we talked to a number of different people, and there was several different opinions about what had happened. And that because of that, the results that we get from our testing may not actually be representative. So what we did is we had samples obtained, because we had obtained samples using both methods, we submitted samples from the same soils or soil groups to see what the results came back as. And here's what we got back. So what you'll see here is a comparison of our group 2 or sand triaxial results, the non-cohesive till, and the silty clays or group 6. What you'll see here is the blue line, the upper blue line, are the results obtained from our PQ tests. The red is a result of sampling, is our sonic samples. So we did our sonic samples, and then we found very, very close each one. And funnily enough, the sonic samples were ever so slightly below the results of the tests obtained from the PQ were higher than those from the sonic. Yes. So based on that, we continued using, and here's a summary of what we had. So for each sample, you can see for each soil group, we had PQ tests, samples tested from PQ and Sonic, and you can see the variation here. As we said, as shown in the previous slide, you can see that the Sonic samples were slightly less in friction angle than the samples obtained using a PQ method. There was a couple of degrees difference, but we did see a lot of variability, it seems, with our cohesion. Once we had completed all of this work, we started looking into, we carried out a literature review, and we wanted to know what's being used in industry. Okay, so we did a literature review of the combination of development reviews and work that TTC has carried out. And we found that for non-cohesive soils, friction angles ranged from anywhere between 28 to 30 degrees to upwards of 38 to 45 degrees. So for a non-cohesive soil, there was quite a range in our literature review. With cohesive soils, we found that the friction angle ranged from about 20 to 40 degrees. And what we also found is there's very little information on cohesion values that was provided in the literature. Okay. Now, based on our test results, we looked at the non-cohesive soils and said, what's the average friction angle range? And we said it's somewhere between 40 to 43 degrees, which is the upper range of what we saw within the published literature. For cohesive soils, we found the same thing. We looked at it and we said, okay, what's the friction angle that we actually measured? Again, if you recall, we were looking at 32 to 33 degrees. That's about the mid-range of what we see up in here from various literature sources. And then our cohesion values, our range was between 13 to about 30 degrees. But again, in the published literature, there seems to be very little information regarding cohesion. So then we compared, we looked at and said, okay, what are design engineers recommending? Okay, and this is where our summary table comes in. Again, we looked at, I think we've got 4 different soil types here. We've got unit weight, cohesion, and friction angle listed. What were in development reviews, what was recommended for various transit projects that was carried out throughout the city, and what we have here. And it seems that I'm jumping. So our friction angle, what we see from our development reviews, transit projects, and our own physical testing is that we see that the average friction angle for non-cohesive soils appears to be underestimated. So our strength is actually underestimated. The cohesion value, the average cohesion value of soils, there also seem to be underestimated by a couple, by a couple of KPA. The friction values of cohesive materials, they're not bad. They're fairly close to what we had anticipated or what we measured. So in general, what we see is we see a trend that as designers, we seem to be underestimating the friction angle of non-cohesive materials, but that we're actually getting the cohesion, we're underestimating the friction angle of non-cohesive materials. We're also underestimating the cohesion values. But what we did notice is that we are reasonably good at getting cohesive materials. So a silty clay, we get relatively decent values, and we are good at estimating those values. So here's our summary now. Here's what we're talking about. So based on the comparison above, the friction angle, I think this is just a repeat, okay? Where the non-cohesive soils are underestimated, the cohesive values are as well underestimated. But the cohesive soils, the friction angle of cohesive soils, is very close to the averages that we were measuring. So we're just going to run in through some comments and some conclusions at the moment. We're moving along quite fast here. So the established soil groups that we created, they give us a really good method of classifying soils and establishing where we are with our materials. There's a wealth of data that we have that we've collected that we haven't presented here, but we do have other data. And it's good, like I say, it's a good way we can classify these things. The sonic sampling provides a quick drilling method. And if you're going to run some triaxial tests, it's also very good as well, because as we saw, the results from the PQ samples and the sonic samples are very, very close. The sonic samples also allowed us to get samples of the sands, whereas when we did work with the PQ, most of the sands and the silts, they were washed out, but we did get really good samples back of those materials using the sonic. With our literature review, we found that the non-cohesive soils in Toronto, they're at the glacial tills, they're in the mid to upper range of the published literature. That's our test that we did. The friction angle of the cohesive glacial tills, again, are in the mid-range of what's been published, and that there is a lack of data in the cohesion values within the published literature. And again, this is going back through our comparison, where we are underestimating friction angle for cohesive materials and the for non-cohesive soils and the cohesion. Somehow I'm getting things jumping around again. Technology is not being friendly with me today. Where are we? Yes, here we are. So again, like I say, we found that the friction angle of the non-cohesive materials and the cohesion of cohesive materials are being underestimated when we look at what's being recommended and is in the published literature. With the friction angles of cohesive soils, we're getting it right. We seem to be doing a good job there. Everything's jumping out at the same time. Sorry about that, everyone. It's suggested that characterizing the soils using the grain size and the Atterberg limits, along with a good understanding and a good database, we can get a better understanding of our soils, especially the glacial ones. And we have now created this database, and like I say, oops. What needs to happen is things need to be consistent in your classification process. If you misclassify, and we'll talk about that in a minute, if a material is misclassified, it causes some problems in your database. What we also say is that although we have a database here that we can use for design, I would recommend that it be something that's been used for preliminary design. You still need to consider doing some sort of site-specific investigation and testing, okay? And I think these databases that we're creating are going to give some comfort in selecting soil parameters. There we go. So some ideas, some suggestions for your consideration is geotechnical engineers and scientists, always review your soil samples in the lab. Always, pardon me, always select representative tests of each material to carry out your characterization tests and get the physical properties. These include your typical gradation, Atterbergs, and confirm your visual descriptions. In order to maintain an accurate database, try and avoid capturing these thin lenses or layers of soils. And this happens to everybody at some point in your investigation process, is that you'll get that grain size back that's got that stone in it, and you'll see it jump. And everybody goes, what happened there? You got to be very careful and cautious about that. That can skew your results when classifying materials. Okay. And then double check your results. Look at your visual assessment. What did you see? What do your characterization tests tell you? If there's a discrepancy, run back through your review. Even go right back to looking at the samples in the lab. Look at the sample you submitted for grain size or for characterization testing. See what's going on with that material. See if there's a difference, a change. Was it what you expected? Okay. Make sure you cross-reference all of these materials. If you do that with your physical properties and your characterization tests, your mechanical properties, when you classify them, they'll come together nicely. What are some of the pitfalls that we've come across? And again, this is misclassification of a soil is one of the things. It can result in an incorrect placement of both the physical and mechanical properties. And it'll also give you a wider range when you're looking at your ranges and your averages. It'll skew your averages when you're doing your investigation summaries for both the investigations, the design reports, and even in your baseline reports, okay? And one suggestion we have as well, and we found this to be interesting, is to always take your characterization test or conduct your characterization test on the same sample you submitted for your advanced or mechanical properties testing. Many times we will take a sample that is representative, and then we take another sample for triaxial testing or consolidation testing. There may be some variation between those materials. And I'm back to my technology gremlin. Yep. Apologies again, my technology gremlin is jumping around here. So we have a couple of examples here, if I can ever get back to it. Here's one here. So the classification, again, based on our visual, we get silty clay with sand, typical classes. This is an actual example from one of our logs. But then we have what is now returned as a plasticity index of 1. We got a PI of 1 here. Grain size, you can see what it's showing you. It's showing you something that's in a silt. Maybe it's a silty sand, sandy silt material, right? And looking at this unit weight or density, it does not match as well. So what you have is somebody's going to have to go back, take a look at these values here, take a look at the descriptor, reassess this soil, and perhaps this soil here needs to be modified. Maybe there was a layer that was captured up in this area, okay? Leaving this in, it will skew the results, like I said before, of all of your results in your summaries, okay? This soil should be reviewed in the lab, and the logs should be modified to make sure that everything is in agreement, okay? Here's our misclassification part 2, okay? We submitted 2 samples for triaxial testing from the same run. One had a set of characterization indicative tests carried out, typical moisture, grain size limits, etc. If this was to be considered representative for both, and we had not tested the second sample for moisture, grain size, and limits, we would have misclassified, or this material would have been placed in the wrong or incorrect soil group. And I can show you here what we have. So this was our first test from the upper portion of run 17, right here. And this comes up as a sandy silt till. And then lower down we have, you can obviously see with the PI what it is. It's it's a silty clay till. 2 different materials from the same core. Just be very cognizant that you don't want to misclassify, because if you do, you can see where it would change your ranges in your final reports. So what's our next steps with all of this information and data that we're collecting? For our mechanical properties, we're looking to use all the triaxial tests to calculate parameters for each soil group. We're looking at some of the parameters for finite element modeling, and you can see some of them here listed on this side: dilation angle, Poisson's ratio, reference moduli, as well as the RF and the M number. So stay tuned for that. We're still working on that one. Also by soil group, what we're looking at is what's our initial void ratio. I think we saw some of that earlier on. We have some graphs of the initial void ratios from consolidation tests. We have the moisture content, which I showed you earlier. And then we're looking at also probably including something about hydraulic parameters as well, and the permeability. And that comes to the end of our presentation. I'd like to thank you. I'd also like to thank the Toronto Transit Commission for allowing us to present our findings.
Okay. Thank you the presentation, and now we have more time to have a question. So please send a question to the question, and we are going to try to incorporate all of your question and to the presenter, and hope they can give us some clarification or some advice. Okay, and now I have some questions. The first, I just let all the let the attender understand. This presentation has been recorded, so the video will be presented in the link of the CGS SOS the portion. So you can have access after this presentation. Then you can see to see more information if you need. And also we are going to also upload the PDF file of this presentation in our website of the society. So you may also get access into that if you wish. Okay, and now the second question is regarding the database you introduced in the presentation, and we know the database has collected so much information, and especially through the different subway line as you introduced. The question is a TTC planning to open the access of the database to the public, and for the public have a way to see them or maybe can utilize them. So I think this is a question probably you can answer first.
Yeah, we are hoping we have been allowed to publish our initial findings with regards to friction angle and cohesion within CGS. We did it at GeoVirtual last year. The plan is that we can hopefully publish some more information, and that's why I said in the one line there for the finite element, finite difference parameters, to stay tuned to 2021 because we're still working on that one. So hopefully that we're allowed to publish there as well. And then as for so that would be your more mechanical properties. As for the other properties, yeah, we by all means, if anybody has a question about it, they can certainly call us or contact us.
Can I add just actually what I would like to tell during this presentation we done. Like most of tables you saw before, summary tables, it's everything in our paper published in GeoVirtual 2020. So it's published information and you can use it.
Yeah, sure, understand. I think the hope probably is for the public access. I think it's more than there's a kind of the database to be accessed in the industry. One of the most popular the database is for the MTO, the geocaching report. But of course, they provide only the hard copy of the load report. But probably that's one of the object TTC may consider, and just open the factory report and for the people who are interested and to be used if it is possible. Because I know as you present, it's hard to get it to collect so much information, and as also every stage of this data process, including the sampling, they are very important because every procedure is linked together, may cause an impact for the next stage. So I do believe those data will be very interesting for the engineer to be used. And also, as you recommend, the parameter or this kind of data can be used for the preliminary design. And of course, site-specific investigation, of course, is still important. But anyway, I think that, but it will be very good contribution to the industry for the geotechnical engineer to use.
I just would like to add one more thing. Actually, it was a huge challenge for us for this 2 big project and the rest of project just to combine all information together and make all this stuff. And the main point is we, like in TTC, we described, review all about 8,000 samples before we send for indicative tests, advanced testing, etc. So main point it was just review and properly describe, and then confirm our visual description is matched to lab testing, because this one kind of the source all misleading and etc. And for this 2 big project, it was a big challenge for us, and we reviewed all samples.
Yeah, sure. Okay, and the next question is regarding the range of the data which presented. And the question is, one of the attendants, he has notified that the average distribution, standard deviation, and so on the angle of the angle of the internal friction were based on the angle itself. However, it should be also analyzed based on the tangent of the tangent of the angle. I think this is I'm not pretty sure about the detail, but however, I believe that's related to the data which you presented. Maybe you can just have some comment about that.
So I just missed a little bit what the main point is, like what the question is.
I think the question is for those data, of course, I believe they are developed based on either by the Mohr circle of the effective test rates. But also the question just asked, can all the analysis also based on the tangents of the angle?
I'm not sure.
I'm a little confused about tangent. So it was pretty. So what Jeffrey presented, we have 3 approaches. One set, like if you just Jeffrey, who right now, can you show the screen? Go to the page 20 of slide. See still, I can just the presentation.
Yep. Let me just flip.
Page number 20, slide 20.
Yeah, this one here.
Yeah,
yeah this is the tangents here to the Mohr circle.
Yeah, so this one, by the way, it's like what Jeffrey no, it's the ideal perfect test. Guys, in many cases, you don't get so nice tangent to three circles. It's first of all, yes. Secondly, what we found, we have, like we told, we checked one by one. That means each set separately in calculated friction angle and cohesion. Then we combine all Mohr circles for the same type of group and make some envelope average for the next slide. It's like 421. Yeah. Yes.
Yeah, so this would have been for a single set of tests for one sample. So you got 1, 2, 3 circles, and then the next set is where we, like Dimitri said, where we've grouped them into. This is all of the triaxial test results for all of the samples for the same group for both downtown and Scarborough.
And the last one, it's stress path, and then it's like so we took maximum Q prime, P prime, like it's sigma 1 plus sigma 3 divided by 2, yes, and we put these values. And what by the way, this one first time I realized, because all literature say, oh, cohesion for clays in effective stress is 0. At some point, when I start reviewing all these charts, oh, right now I start understanding why everyone in any book say cohesion in effective stresses 0. Because maybe professors, I don't know how, or researchers use just stress paths. They didn't rely on more circles or separate or average. And then, you know, it's exactly what we showed during our summary tables. There is differences, depends how you're going to analyze your tests. And like you have deviation. So tangent, because some people can say, oh, tangent, you should go to 0 and you go with small stresses, confined pressures during the test, and it's going kind of not straight line, it's going to be curved line. Yes, but guys, just keep in mind, when you apply, okay, this one will come to the lab. If you work in the lab and somebody asks you, just apply effective, like confined pressure, 20 kilopascal or 15, you already start dealing with like machines, like how exactly you can keep this 20 kilopascal, because it's during like compressor working, it's going a little bit up, a little bit down. So really, you cannot make just assess what exactly, if it's really curvature or not, because it's already technical issues. And this one, everyone who did work in the lab, all lab managers like in Golder, in GHD, in Wood, they do know very well. So sometimes engineers asking something, but they don't know limitation of specific equipment. And this one, you stuck with technology.
Yeah.
Sorry, maybe I'm answering questions, maybe not.
Yeah, I think the interpretation of the data, I think have to consider many things as you explained. So I think that anyway, we can go to the next question, and if the person still have a question, I think he is welcome to contact you for further discussion. Okay, and we have so many questions now. But I pick up I try to group them, but anyway, the one question is regarding the sampling methods. Has the Shelby tube data be included in the database?
Oh, samples obtained using a Shelby sampler?
Yeah.
I don't believe we had carried out any Shelby samplers because
I think we did several, because you just have to keep in mind, when we drill for Scarborough, definitely we cannot pick up Shelby's, no chance.
And that's what I was going to say. Scarborough soils, they would not. They're too
hard to dense,
compact and hard. Yeah. But the relief line, we may have had a couple of samples.
Yes, from relief line, yes, but we didn't have a chance. It's like really you start delving so deep. Compare if there is Shelby's difference. It's like, guys, it's like next level. We just combining this data. It was big headache, like, you know.
Yeah, one of the reasons that we did. Sorry, one of the reasons that we did the sampling comparison, as I've just thrown it back up on the screen here, is that we were the PQ. We were losing material. So on one of the projects, because it was such a rush, we were actually losing sample with the PQ method. And we were only getting cohesive materials back. And the Sonic, where we could do a PQ core in about, it was probably, I'm just trying to remember now, I think it was about 6 to 7 days for us to get the full depth PQ core. Whereas doing the same thing with a Sonic rig, we could do in 2 to 3 days, depending on depth. Now we're talking, I'm just talking specific to Scarborough's project. We were doing 60 meter deep Sonic tests, and they were taking us between 2 to 3 days, but the PQ was taking us upwards of about 6 to 7 days to get to the same depth. So with the urgency of the project, the way it was at the time, that's where we did this comparison. It would be nice, yes, to compare the Shelby samples with these results and to see how it all comes together. But again, the Scarborough soils were so hard and dense It would not. I mean, most of the blow counts out there were 100 plus.
Yeah.
So you could not push a Shelby in that material.
I just would like to add one more point regarding this one. So initially, when we started dealing with Sonic, and everyone thought, oh, Sonic, it's totally disturbed samples, and I couldn't understand why. What's the reason behind that? People talking about it's totally disturbed, and then I realized actually disturbance or quality of sonic samples literally depend on specific crew of the drillers, because we use several drill crews, different companies. Once we drilled with one guy, because during Scarborough and downtown we have 3-4 consulting company, different consulting company was during this project, and they use different drillers. And once we start drilling Sonic, and I come back to the lab, just review samples, just first 2-3 boreholes. When they opened, it was literally first 20 feet, pure powder. And I was, wow, what is that? Powder. I couldn't understand what is that. I start looking, all of a sudden I just found some gravel. When I braked, turned out it's like cooked till. So drillers who drill it, they totally destroyed the soil to condition of powder.
Yeah.
I was freaked out. Anyway,
yeah,
it's just smoke.
Yeah, I think this is a very good thing because we are talking about, your subject is dealing with the material in downtown Toronto, and as we know, most of the soil in the downtown area, they are generally steep to very steep to hard, the cohesive material, as well as dense to very dense, the granular material, no matter what kind of the soil groups we're talking.
Yes.
So the next question is as one of the presentation, you compare the result of the database of the interpreted data with some literature.
Yes.
So are those literatures those literature, the geotechnic condition described in those literature is locally or Canadian soils, or is international soils? So can you have some comment about that?
Sure, and I've just thrown the screen back up here where we say, okay, what are being recommended? So these recommendations you'll see in the list here, they were strictly from development reviews that were submitted to TTC. So these are any developments that are within the city of Toronto. And also when we say transit projects, it's any transit projects within the city. So these two comparisons were done specifically for projects within the city. And that's where so everything that you see here would be for City of Toronto.
Yeah. Then how about the reference? Yeah, you have a comparison with the reference literature, and there's some difference. So how about those literature? Are they the soil collected from the worldwide, or is it also the local soils in GTA or Canadian and so on? Just give idea about the soil condition of the reference literatures.
I think it was from this one here.
Can I just, in addition of what Jeffrey told, so we took development review, we took transit project, and also we compared, remember in our article, table number, just open this PDF, so table number 7, we also used Hansen, Meyerhoff, and different manuals. So EPRI, Thorburn, Meyerhoff, and the structural foundation design manual. So we took different talks, not just from Toronto area, but we took just different books and sources, like worldwide, like what ranges people taking for different types of, based on SPT, for example. Okay.
Yeah. Well, what we had tried to do is we had tried to focus in on the Toronto area. And like I say, that's where this, this chart comes from. This is specific to Toronto. But then, we didn't include it in our presentation, but we did look at some of the, everything's disappearing on me. Like Dimitri said, the Meyerhoff, the EPRI manual. How did our results compare to those results? And that we can find in our GeoVirtual paper.
Okay. And the next question, I combine several questions together. I think that the main question is for your for the grouping, do you and the comparison, can you also include some typical data we can collect, especially for the N values and for the cohesive material? Yeah, of course, is the upper limits, the data, those, and probably also because we are dealing the material in the downtown area. Then, of course, the OCR, over consolidated ratio, may also is one of the factors to cause an impact for the parameters. So, just for your consideration, maybe you can also incorporate those information together and with the different interpretation data. I think they will be also pretty helpful for the geotech engineer to understand the properties.
Can I answer, Jeffrey? And you add.
Yeah, that's fine.
Yeah. So actually, it's exactly what we are planning to do and what we're doing actually right now for next conference in Niagara Falls. We are doing exactly what they asked about over-consolidation ratio. All these parameters is going to be combined for all Plaxis and FLAC software, and definitely more parameters such as OCR or E50 reference, UR reference, which generally used in software. We are going to incorporate in this one. And I think that, and Jeffrey, maybe you can add.
Yeah, no, and that's a GeoVirtual plan, and yes, it would be nice also, and that's one thing we do have to look at still is where you're cross-referencing, say, N values and or water content with some of the strength parameters, friction angle, etc. And that's where we, like I say, if you look at the GeoVirtual paper we did, there is a comparison in there with our results to some of the other published data that, Terzaghis chart and that. So we did try and do some comparisons there, but it would be nice to be able to correlate what we have. And that's going to be, right now we're working on some of the finite element and finite difference parameters that can be used. And then hopefully we can get into some of the other stuff as well.
And I just would like to add, because I think people or persons specifically ask about correlation between SPT and parameters. An issue is very simple, because definitely most of soils in GT area is glacial deposits. When you're moving towards waterfront, you have softer, and definitely you can be maybe going to do comparison SPT and parameters. But for most of glacial deposits in GT area, your SPT in like 95%. It's like more than 50 blows counts, or 45 or 50, you understand me? So you cannot compare it, because it doesn't make any sense. Like everything more than 50 blow counts, period.
Yeah. So probably anyway, you can think about how to correlate the result, the advantage with some popular, the general popular, the parameter normally we use. I understand N value may not be representative, but however, N value is one of the popular data we always can get from the sand investigation. And also, as you also mentioned, that water content, I think it's also a good index to correlate those parameters.
Yeah.
Okay. And the next question is regarding the in-situ test. And we know many pressure meter tests or dynamometer pressure, especially for the pressure meter test and even the CPT test has been carried out in several projects of the several subway projects.
Mm-hmm.
Do you have a plan also correlate the result for those from those in-situ tests and correlate with some maybe for the current your interpreted the engineering properties or maybe with something else? Mm-hmm. Can you explain it?
Yeah, there is, we would like to be able to do that. And I think we've started, I mean, with both projects, we did a number of pressure meter tests. We also did a number, and the other thing we'd like to look at as well would be even looking at shear wave velocities as well, because we did a number of downhole tests and cross-referencing maybe the downhole shear wave velocities with some of our values, or surface wave MASW testing with some of the values that we have, and how does that all interrelate and correlate? But that's
it's exactly our
coming
goal.
In the future.
Yeah. No, it's exactly our goal. I hope.
Sorry, Dimitri. With Scarborough Line, with the soils and the condition we encountered, CPT was very impractical. We did try it once out there at a creek crossing. We were lucky to get 7 feet in the ground before we actually started lifting the rig up. So we abandoned that idea. Downtown relief line, I think some of the soils probably lended themselves to some CPT. I can't recall if we did any there, but with some of the work we're doing in the waterfront right now, the hope is we are also obtaining some TRAXIL results or samples. Hopefully they get some good results back, and then we can start cross-referencing some of those CPT values. But at the moment, I think one of our next steps would be to look at the PMT and see how that interrelates with all the results we have.
Actually, I just would like to add to Jeffrey what told right now. Actually, we're doing exactly right now. We're doing that. We're trying to compare PMT results with E50 reference, EUR reference, whatever people using in final element analysis. Exactly, it's we right now in the middle. We're in process. So I hope we can make this kind of comparison, because based on like whatever we see right now, sometimes it does work. You can use PMT, but sometimes absolutely off. So, and like when we're doing our development, we sometimes start using these numbers, and no, it doesn't work, guys. Okay.
Okay, and okay, now the next question related to the interpretation of the advanced test. One question is, can you comment some difference between the shear strength parameter interpreted by the method of the stress test and the Mohr circles? I remember during your presentation, there's some difference. But however, those difference is can you also compare with the literature? Some published literature about this difference.
So this is is this the cohesion values?
No,
generally, yes. Yeah, generally, yes. Or cohesive, yeah. For cohesions.
So for the cohesion values. So we're talking, I'm just trying to find it here.
Just question. So the question is, if we bumped into encounter in literature comparison between Mohr circles and stress pass comparison, how different results. So like personally, me, if you ask me, I searched maybe the last 15, 20 years. I've never ever seen it. Never. So maybe somebody made it, but it's buried somewhere under a huge amount of papers. And I try to find, because it's exactly the point why I realized first time, I couldn't start understanding why everyone talking about cohesion in effective stress is 0, because I could, but it's only like this big project, I could literally sit down, summarize all data, and to see differences. But I never ever could find any articles or textbooks or whatever explaining these differences. Everyone talking about generic approach, like very generic, and then immediately start dealing with numbers. But no one, I never seen an article about that. If somebody does know, I'm really, guys, appreciate you can send to me.
Yeah.
Okay, then the following question: what's your advice for to interpret the engineering property between the stress path and the Mohr circle method?
Okay, go ahead, Jeffrey. You and then
really, I mean, it's up to the individual engineers to make that call on the designer. I mean, once you've done your analysis, personally, my suggestion would be to do it both ways and see what you get, and then you can compare. But again, it is up to the individual designer and the engineer who's doing the analysis to actually pick a method and stick with, or, I mean, sometimes there's companies that will say we only do Mohr circles, sometimes they'll say stress path. My suggestion personally, I think you would have to look at both and see what you get, and then you would have to, look at what the results are and how you are with those results.
And I just would like to add, just definitely it's up to individual or engineers to decide what number to take into account. We just present it in GTA. And by the way, just keep in mind, this one kind of, every time I'm just repeating, we did so much analysis for GTA area, and I'm pretty confident. If you move 300 kilometers north, south, west, east, I have no idea. This reason I've never ever relied on any like literature textbooks. People, okay, this one Celtic Lake 25 degrees whatsoever. From where came it from? I don't know. If it may be from middle South America or Middle East or from Africa, it's not relevant at all to specific region you are working. So it's, by the way, any textbook saying, guys, you have to accumulate and take local values, whatever, because if you move to Ottawa and you have lead clay, it has nothing to do with our clays. If you're moving to Sarnia, we have blue clays, also not relevant. So it's like, but for GT area, I feel pretty comfortable with these numbers. Right now, it's so much numbers. And by the way, I just would like to tell you, in our database, we just analyze here 180, 200. But in our database for C5, we have about 350 triaxial sets, like from Shepherd projects, from TYCC projects, from different projects, much more. We just talking about like Scarborough and downtown Line.
Yeah. And what we've been able to do with the data we have is that we've been able to use the same classification, same methods. We've done both Mohr and stress path to analyze triaxial results. And we're using that now for example, for the Bloor-Young improvements. There's work being done in the Bloor-Young area. And again, we're using it for the waterfront as well. So that's going to hopefully add to our database and our information.
But I just would like to add in general sense. So main point is, like idea was specific physical property, packing of the particle, plasticity has to be addressed or correlated to specific mechanical properties. So this reason, when we made this presentation, the main point is like, you cannot just rely on visual. It's the same, I just make like analogy, like you came to the doctor, he made blood test, and then the doctor looking at the results, you know what, blood test not good, but don't worry, you look so nice. So don't worry about blood test, just mean guys, we carry out the test. So what's the point? If I can do everything visually, don't do tests, and then it's pure art. Everyone is right.
Okay, I do agree. As a geotech engineer, we have to fully understand the method or parameter, the meaning of the parameter we consider. We cannot just adapt the number without any consideration.
Yeah.
But anyway, it's a pretty good discussion.
Yeah.
And I think one of your conclusions said, based on your interpretation and the database, some parameter may be underestimated.
Mm-hmm.
So what's your advice for the consultant for their design work? Where these the kind of the conservative parameter may cause significant impact for the cost of the project or not?
Yeah, and that's one thing that we did find is that we, for some reason, I we haven't really delved into it, but we seem to have a good idea for clay soils, clay type soils, cohesive soils on friction angle, which is interesting. But again, the cohesive intercept doesn't appear to be really well understood. And then the friction angle of non-cohesive soils, we are underestimating, and that seems to be something that is underestimated. What designers have to be careful of is we're giving what our results are.
Mm-hmm.
But then what they have to be careful of is what's I believe Dennis Becker has been talking about for a few years is what is the value that based on your results should you be selecting? What is the characteristic value of that soil? And that's something that we started talking about internally ourselves as to, okay, yes, you've got a friction angle of, a measured friction angle in a sand of 45 degrees, but is it reasonable for us to say, let's use 45? Maybe what we need to do is to say, okay, we'll take a certain percentile of that, okay, and use that as our value. I know at times we've seen some people use the 10th percentile for some values. So, or like you're running things around and you say, okay, well, we use that value. And I know we've talked internally, the European code has a method where you can find out, you calculate out your averages, but then you take what they have as a characteristic calculation, and you can use that for your design. So there's those types of things that will need to be reviewed by the engineer. And of course, it's going to come down to what site you are, where you are, and your own experiences. But like I say, we do find that the sands and silts, gravels, they do seem to be underestimated. We do have over-consolidated materials. They do have high densities, right? So, and then again, it comes down to a designer's choice.
Yeah, so what every time we was surprised when we reviewed development review or something, you have refusal in sands, silty sand, teals, and etc. If people providing 30 degrees, guys, 30, it's a response angle. It just you put your sand already 30 degrees. So how come you getting refusal and you getting just 30? So it's over conservative. So definitely engineers should take into account all factors and etc. But just 30 degrees, then we don't need to do any tests. 30 degrees, factor safety 10, end of story. We've solved all problems. Why do we need the investigation at all? No, sorry,
Yeah, I understand. Yeah, that's the reason why I pay for the consultant work to get a more optimized parameter. Okay.
Yeah.
And the next question is does your interpretation include the result of the director shear test?
We did do some direct shear tests. I'll leave that one to Dimitri. Did we include that?
Yes, but we never ever analyzed because we didn't have enough data, but it was pretty good comparison. It was maybe 5-7 direct shears and from the same type of material, triaxials. And it was pretty good, like again, plus minus 1-2% of friction angle, pretty good corresponding. But because first of all, as everyone know, direct shear, you predict specific shear planes. That means you kind of, in many literature say it's overestimating because you're forcing specific, not weak surface or something. And we did several times. It worked pretty well. Just do know some countries, for example, use only direct shears, and based on direct shears, they're doing all recommendation, not reaction, because it depends on how wealthy country and if you can afford so expensive equipment, because direct shear is much cheaper. But we never ever dealt with deeper like comparison direct shear and triaxials, like, you know. But based on 5-6 tests, it was pretty good. So almost identical numbers, but we never will include in our article.
Okay. The next question is raised by the structural engineer. He said, for his design work, because he doesn't have much knowledge about the geotechnical engineering, then how to utilize those characterize the value as presented? Does he need to consider kind of the deviation, say 5 to 10% difference if compared with the average value as presented?
Jeffrey, you, me?
So just to confirm, so we have a structural engineer who's looking at the average values and how to consider those values and the standard deviation that we're presenting. Is that the way I understand that one?
Yeah, yes.
My suggestion to a structural engineer is to hire a geotechnical engineer. For the interpretation.
No, actually,
plug for our geotechnical engineers. But I think for a structural engineer, I think what it comes down to, again, it is it does fall within the geotechnical. And yes, you can look at those parameters and say, okay, yes, we let me flip to those average values somewhere. Well, here's some here. But you can say, okay, yeah, you can use those values as an average. But again, it comes back to the characteristic values. So these are averages, which, like I said, we're underestimating our granular materials. But then somebody's got to select at some point a characteristic value, whether they have to consider the standard deviation or not. That is up to them. I know when we were working with the Scarborough line, we did do a presentation table, which is a very large table of all of our values, and then we gave the 90th, 50th, and 10th percentile as well, so that the analysis could be carried out, and then the parameters could be varied. We could see what was going on when they started doing the liner design, and they could vary things around. But yeah,
okay.
so
yeah,
okay.
And we have a very limited time left, but just a last question. As you present, is where your soil classification system be modified based on the available data and based on the result of your interpretation?
So the classification system or the grouping that we've created will be modified eventually. We already know right now, working towards the lakefront, we're already finding lacustrine soils, like we showed in our example, that don't match within the soil. The physical properties are not matching into one of our 7 soil groups. And yes, we will most likely have to modify this. Maybe that we have to add something where we call it a group 8 or 9 or a subgroup somewhere.
Okay, something like that. So
yeah, it's something so that we can identify it and say, okay, we've done a grain size. It fits with our silts, but our plasticity index fits with the clay. We can't put it as a G6. We can't put it as a G5. So we may introduce another soil grouping and say it's a lacustrine style deposit. So this is where it would fit. But that's future work.
Okay, sure.
For now.
Okay. So Dimitri, any additional notes?
No, I just think Jeffrey just answered, and just maybe just small ones. Actually, maybe, but we need to get more data. Maybe this lacostream deposit with high plasticity but matching envelopes of gradation, maybe it's matched for mechanical properties to G6, you know, like friction angle, cohesion. And by the way, this reason, unified classification don't look hydrometer. It just look SIG200 finds Atterberg limits. And maybe based on our data, we'll see, oh, you know what? These new lacostream deposits with envelope like seals, but plasticity as a clays, maybe mechanical property, it's exactly like a G6. So, okay, it depends. We need to review and just work on that. I don't know right now answer. I don't answer.
Okay. Yes, I think that's the end of the question and the answer, and we are in a perfect time to end this wonderful webinar. And I know still have some questions cannot be answered, and probably after our discussion, the attendant may also have some additional questions we like to discuss with you. So anyway, this is a very good the process and the contribution to the industry. So I think all of the geotech engineer suppose your approach, and also expect to have more opportunity for you to share the result of your research and or interpretation. Thank you, and thank you for all of your attendance. Now I think it's the end of the webinar. Thank you. Now can enjoy your wonderful lunch. Thank you. Bye-bye.
Thank you.